Hello students, myself Mohammad Wasim, Assistant Professor in Mathematics, Art Science Commerce College, Badnapur. As you know that we are studying about application of Laplace transform, in which we are studying about application to differential equation. Now, in this chapter, we have studied the theory part, and which is very simple theory part for this chapter, and we have solved some very basic examples which are depend upon differential equation, and by applying Laplace transform and inverse Laplace transform we have find the solution of that differential equation. Generally we come across a very complicated differential equation which is not easily solvable and which has a very complicated method of solution. At that time we apply Laplace transform and convert that equation into algebraic equation, and we know various methods to solve algebraic equation. Now today we are going to solve one more example which is somewhat complicated but easy. Whenever we try to solve such type of example, we will get or we can apply very easy theorems which are based from first and second chapter, that is Laplace transform and inverse Laplace transform. If we apply that chapters to such problems, we can easily solve the solution of such examples. So we are studying about inverse application to differential equation. We are studying about application of Laplace transform to differential equation, and the example is given as solve the given differential equation by using Laplace transform. And which is as follows: y double dash plus 3 y dash minus 3 y dash plus 2y is equals to 1 e raised to 2t. 1 minus e raised to 2t. I think it is visible now? Yes. Solve the differential equation by using Laplace transform, and equation is as follows: y double dash 3y dash plus 2y is equals to 1 minus e raised to 2t. Now we know that the method to solve differential equation by using Laplace transform is as follows. We have to apply Laplace transform to such equation, and after applying some theorems, as per our convenience, we can convert this equation into algebraic equation and find the solution of that algebraic equation. And after applying inverse Laplace transform, we will get the solution in the required form. So apply by taking Laplace transform on both sides, we will get Laplace transform of y double dash 3y dash plus 2y, Laplace transform of 1 e raised to 2t Now, since we know that Laplace transform satisfies linearity property, so we can distribute the operator over y double dash, then minus over 3y dash plus then over 2y. Similarly, we can distribute Laplace transform to 1 and e raised to minus 2t. So we can write it as follows: Laplace transform of y double dash minus, taking 3 constant outside, Laplace transform of y dash plus 2 taking outside, we will get Laplace transform of y is equals to Laplace transform of 1 minus Laplace transform of e raised to 2t. Now, since we know that Laplace transform of differentiation, or we can write it as by, since linearity property holds. Since linearity property holds, then we can distribute the transform operator to each term. Now, by applying Laplace transform of derivative, we will get s square y of s minus s y of 0, then y dash of 0 for this particular part, minus 3 Laplace transform of y dash, again Laplace transform of derivative, so we will get s y of s minus y of 0, correct, plus 2 Laplace transform of y would give us y of s, Laplace transform of 1 upon s, and Laplace transform of e raised to t is 1 upon s minus 2, and which we have done in Laplace transform. Now, I missed something in question, and that is the initial conditions. And the initial conditions are given as follows: y of 0, initial condition y of 0 and y dash of 0. Y of 0 is equals to 1 and y dash of 0 is equals to 0. So, by putting this value in the required equation, we will see some changes, which is as follows: s square y of s minus s y of 0. Y of 0 is equals to 1, so we can write only s here. Now y dash of 0 is equals to 0, so minus 0 minus 3 sys as it is minus y of 0, and y of 0 is equals to 1, so we can write 1 plus 2 y of s 1 upon s minus 2, correct. Now we will see, we can take y of s and y of s common outside, we will get y of s is equals to s square minus 3s plus 2, and now minus s minus 3 and into minus 1, that is plus 3, correct. We have minus 3 into minus 1, that is plus 3, and from this side we will get minus s only, then we can find 1 upon s minus 1 upon s minus 2. Similarly, if we save this into right hand side, we will get s square minus 3s plus 2 is equal to 1 upon s minus 2, minus s becomes plus s, and plus 3 becomes minus 3. Now we will send this to right hand side. This is multiplication. So it will be s square 3s plus 2 minus 1 upon s minus 2 s square 3s plus 2 plus s minus 3 s square 3s plus 2. Correct? And we have the required solution for y of s. Now we will convert this solution into variable t by using or by applying inverse Laplace transform. Now before applying inverse Laplace transform, we will break this quadratic equation. We will